So today I am going to discuss about the measurement of superconducting Transmon qubit. So before going into the measurement, we should look into the Transmon. So this is a Transmon qubit. So basically nowadays researchers are use flux tunable Transmon. So basically it use two Josephson junction. These are the two Josephson junction instead of one Josephson junction. So Josephson junction is a basically it consists of two superconductor separated by a insulating material. So this is a Josephson effect. It is a phenomena where the supercurrent flow between two superconductors separated by a thin insulating barrier, and it's follow the quantum tunneling effect. And when we use two Josephson junction instead of one, so it is called as SQUID, also known as superconducting quantum interference devices. So it is made up with superconductor. So if we put a SQUID in a magnetic field, as the superconductor are diamagnetic, the material will oppose the magnetic field, and in the empty space, this space, there will be trapped magnetic flux. So according to Lenz's law, there will be a induced current in the squid. By this application, we can tune the resonant frequency of a transmon qubit. So in the previous slide, we see that how a squid works. Here in this circuit, so this is the circuit, the flux bus. This is flux bus. Flux bus apply a current, and according to right hand thumb rule, there will be a magnetic field which will operate the frequency of the qubit. So this line. So in more depth, it will affect the effective Josephson energy of the squids, and which is a key parameter of determining the transmon qubit's resonant frequency. So before going into the qubit drive, this is qubit drive and readout mechanism. This is the readout part. This is readout resonator. We should look into strong and weak coupling. So strong coupling. So it's ensure a rapid and precise control over the system. So there is a strong coupling between the qubit drive. So this is qubit drive and the transmon. And weak coupling. So they are the two system. Two system means transmon and this interact with each other minimal. And there will be almost no energy transfer. And so now the qubit drive. So it is useful for state preparation of qubit, or you can say the gate. We can apply gate by this qubit drive. So now the main part arrives, the qubit readout. So readout resonator act as a harmonic oscillator, while the transmod act as a anharmonic oscillator, and their resonant frequencies are detuned. For an example, transmon has a resonant frequency, let's say 5 gigahertz, and resonator has 7 gigahertz. As Transmon qubit is a quantum system, and if we measure any quantum system directly, it will collapse. The quantum system will collapse. So we need to keep in mind that phenomena. Previously, I said that there is a weak coupling between transmon and the readout resonator. So in drive line, we apply a frequency in the range of qubit resonant frequency, and we prepare the qubit state, but it in readout resonator we apply a frequency in the range of resonator. As I previously said that these two frequencies are detuned. For an example, this is 5 gigahertz and resonant frequency is 5 gigahertz and this resonance frequency is around 7 gigahertz. This is an example. So due to the resonance of the resonator, we can see a dip in the resonator frequency. If we measure the output, we can see a dip due to its resonant frequency at its resonant frequency. At resonant frequency, the resonator will absorb all its energy. So we see a dip basically. But as there is a weak coupling between transmon and resonator, this is a weak coupling. So we can see that this is far from the transmon. So depending on qubit set, the dip, the due to the resonator resonant frequency, there is a dip, but the dip will be shifted by the dip will be shifted by the transmon state, the qubit state. So basically, there is a weak coupling between the transmon and the resonator, and depending on the qubit state, the dip will be shifted. By calculating the shift, we can distinguish the zero state and the one state. So we can see the dipped. This is the blue line. This is the dip. This yellow line. There is a two dip. So this is basically from the state of the qubit. This happened from for the state of the qubit, and we can determine that this is due to the zero state and this is due to the one state. And from the difference between two, we can determining the difference between the one level and the zero level.